Now I invite our next resource person for the day, Miss Harpreet Kaur, Senior PGT Chemistry from Bharti Vidya Bhavan Public School, Amritsar, with the total teaching experience of 20 years. She is also a CBSE resource person and has been awarded the CBSE Best PGT Chemistry Teacher Award 2021. She is the teacher guide for the National Children's Science Congress, CBSE Science Fair, Inspire Award, National Innovation Founder for the past 20 years. So I invite Harpreet ma'am to please start with her session.
Thank you, ma'am. Thank you so much. Good evening, everyone. Am I audible and is my screen visible?
Yes, you are very much audible.
Thank you, sir.
The screen
I
is
will.
also.
Ji, sir. I welcome you all to the Faculty Development Program for Science Educators organized by Shikshan Bharti, Bharti Vidya Bhavan. And I'm highly grateful to our Educational Officer, Dr. A.K. Sharma, sir, for providing me this opportunity to conduct the session. In the current session, we'll be discussing about the structure of atom for grade 9. Before I formally start with the chapter itself, first of all, we all go for the syllabus. Whenever we start our session, whatever grade we are teaching, whatever subject we are teaching, we start by looking at the syllabus. And what we look in the syllabus, the list of the chapters, the list of the topics, the hours which are divided to the different chapters, and at the most the weightage of the different chapters. So we hurriedly look on the syllabus. Do we look at the curriculum also? Is syllabus and curriculum the same thing? May I have your responses in the chat box? My dear friends, curriculum is much more beyond the syllabus. As curriculum refers to the knowledge and skills the students are expected to learn, and it includes all that from the experiences of the children in the schools. It includes the learning outcomes, the units and lessons, the assignments to be given, the projects to be given, the resources to be used, the assessments, and the values to be learned by the students. And CBSE has provided this curriculum for the secondary school for the current session, that is 24-25. It's a 43-page document. And my dear friends, kindly go through this document before you start with your teaching. You cannot do the justice to your teaching if you'll not go through the objectives of this curriculum. To achieve the vision of NEP 2020, that is holistic development of the children, and to achieve the desired learning outcomes, CBSE has defined the certain curriculum objectives, like to provide an ample scope for the holistic development, may it be social, emotional, moral development, or the academic development of the learners. Emphasize the constructivist approach rather than rote learning. And then the students, their 21st century skills, they need to be developed. Nowadays, the role of the teacher is not only to impart the knowledge to the students, but to make them sufficient to learn how to learn. As the knowledge they gain today, it's going to be obsolete in coming few years. So their skills need to be developed so that they can survive in the future. They are the future ready citizens. And for that, the teachers, they have to follow the different pedagogies like the art integrated learning, the toy-based pedagogy, storytelling, gamification, ICT integration. My dear friends, this is the screenshot from the syllabus which has been prescribed by CBSE for class 9th and 10th. And see, the first line says about the syllabus. The subject of science plays an important role in developing well-defined abilities in cognitive, affective, and psychomotor domains in children. Now, kindly reflect. Do we really follow these guidelines while planning the lessons, while developing the strategies, while designing the assessments? Do we follow these cognitive, affective, and psychomotor domains? In the syllabus itself, this question paper design is also given. And what this question paper design describes, that the competences to be assessed by the year end, they are the demonstrate knowledge and understanding 46%, application of knowledge 22%, formulate, analyze, evaluate, and create 32%. All our teaching strategies, our plannings, our instructions, and the assessments, they must be aligned to the achievement of this target so that the development of the competences happen. It's not only the imparting the knowledge to the students, but their competences, their skills to be developed. And to understand all these terms, which are described there in the syllabus itself, in the question paper design, we need to go through this Bloom's taxonomy to understand the question paper design, to plan the instructional strategies according to this paper design, to achieve the vision of NEP 2020, to develop 21st century skills, to develop the competencies among the learners. Bloom's taxonomy is the ultimate tool. In the Bloom's taxonomy, 3 domains they have been given as they form the first line of our syllabus. And this is to be followed in all the grades, in all the subjects. It's not only for the science class 10, it's for all the grades as well as for all the subjects. And these 3 domains, they are the cognitive, affective, and psychomotor domains. Cognitive, that is mental skills and knowledge. Affective, attitude and self. Psychomotor, manual and physical skills. That is, these 3 domains, they are dealing with head, heart, and hands. Now, to understand these domains, these are the domains of the cognitive level. It's a hierarchical model to classify the learning outcomes from simple to complex and concrete to abstract. There are 6 levels of cognitive learning, that is remember, understand, apply, analyze, evaluate, and create. The basic level, it starts with remembering, where the students, they need to remember the facts, they learn the definitions. This involves a rote memorization. And after learning the facts, then comes the understanding level, where the students, they can explain, they can describe, they can identify, locate, recognize the concepts. Like the questions of type state the law, name the element, this type of questions, they belong to this remember category. How, when, why, explain, describe, this type of questions in the understanding category. And these 2 categories together, that is remember and understanding, that's the first part in the question paper design, which must constitute 46% of the questions from this level. Then comes the apply, where the knowledge learned and understood by the students, they learn to apply that knowledge in the new situations. Like all numerical type questions, calculations, or where they can apply the concepts in the new situation, in their daily life situations, this type of questions, they come in this category, and this category constitute 22% of the question paper. Then in the third category, which is the 32% of the question paper, that involves the upper 3 skills, that is analyze, evaluate, and create. In the analysis, the students, they Consider the different subparts and then compare those subparts to arrive at the conclusion. In the evaluation, they give their decision, like if A or B are given, which has a higher melting or boiling point out of A and B, which is more reactive, where they need to give their decision and this develop their decision-making skills. And the highest level is the creation, where they describe something new out of the box, something which is not described in their textbooks. So these 6 levels, and they constitute the 3 parts in the syllabus, that is remember and understand, constitute 46%, apply 22%, analyze, evaluate and create, they constitute 32% of this question paper design. So all our instructional strategies, learning outcomes and assessments, they must be aligned with this Bloom's taxonomy as it has been prescribed in the syllabus for the secondary classes. These are the suggestive learning outcomes for the current session on the structure of atom. And these are the outcomes as per the Bloom's taxonomy. These are not the ultimate outcomes. These are just the examples to describe. As in the learning outcomes, the first one is by the end of the lesson, the learners will be able to define fundamental subatomic particles, their charge and mass. This belong to the remember category, the first one, first level. Define, state the laws, that's the first category. Then in the understanding, the learning outcome which belong to this category from this chapter, like they'll able to explain the unit charge and unit mass, describe the fundamental subatomic particles in the atoms of different elements, understand the cause of the nature of the charges on the cations and anions. Like if you ask the students, what type of charge is present on the cation, positive on the cation and negative on the anion. That's a remember part. But why cations have the positive charge and anions have the negative charge? This type of question that belong to the understanding part. Then the fifth objective, as you can see here on the screen, they'll be able to find the actual mass and charge of the atoms or ions. That's the applying part. Then seventh one, which is identify isobars, isotopes, subatomic particles in the given set of atoms. That's the analysis type. Then compare the postulates of the different models of the atoms, evaluation, and then from the given set of the fundamental particles, if they'll represent the different chemical species, that's the creation part. These are the some assessment questions as per Bloom's taxonomy. Again, these are just the examples. Actually, I should have discussed the assessment by the end of the session, but just to make the Bloom's taxonomy more clear, I'm discussing it before the actual topic. The first question, what is the 1 unit charge? Here the student that need to remember the value. So it's the first category, that is remember the first level of cognition. Then what is the nature of the charge on the cation? Remember, why cations acquire positive charge? Now understanding, because here the child will explain that the positive charge is due to the greater number of protons as compared to the electrons. Then fourth question, calculate the number of the different subatomic particles in aluminium 3 ion. Here the student need to apply the learned knowledge that in aluminium 3 positive ion, how many electrons are there, how many protons are there. Then they'll compare the number of electrons and protons, and then we'll find out the actual charge and the different subatomic particles present there. Then the fifth question, arrange the following elements. Like a number of different elements are given. Subparts are there. Students need to go through element one by one and then find out the subatomic particles. And then the student need to arrange them according to their number of protons, their neutrons, their mass number. That's the analysis type of question. The assertion reason questions, they are also the analysis type question in which the students, they break the concept into subparts and then reunite it to come to a conclusion. Then the sixth one is evaluation. If Rutherford's alpha ray scattering experiment, some lighter element is used, would the results be same justify your answer. Now the student's opinion is asked for. The student need to give the decision where justification is asked. That's the evaluation type of question. And then the last one, that is 40 nucleons are there, 18 electrons are there. With the 40 nucleons and 18 electrons, if the student is naming that the element is calcium, then that's only the understanding part. But see here, it's written that represent all the possible stable chemical species. That means it is expected that he need to create the different type of chemical species, like it can be calcium 2 positive or it can be argon. Now coming to the content in the chapter, starting with the atom in ancient times. If we go on dividing the matter to get the smaller and smaller particles, ultimately a stage will come when we all shall come across the smallest particle beyond which further division is not possible. That's the uncuttable part. And this idea of divisibility of the matter was considered long back in ancient times. This uncuttable part, it was named by Indian sage Maharishi Kannar. He was born in 1600 BC and he named this uncuttable particle as Parmanu. And Democritus in 400 BC put forward this term, that is atoms, from the word atomos, which is indivisible, uncuttable. And according to Democritus, everything is made up of atoms. Cheese is made up of cheese atoms. Iron is made up of iron atoms. Clay is made up of clay atoms. So this was an idea which was there in the ancient times also. And Democritus said, according to convention, there is a sweet and a bitter, a hot and a cold. And according to convention, there is color. But in truth, there are atoms and a void. Everything is made up of atoms only. It was stated by Democritus in 460 BC itself. Now, as we all are aware that the size of the atom is too small. It's small beyond our prediction, our estimation. So to make the students understand that how small an atom is, it's beyond our imagination. We can use this analogy that if an apple is magnified to the size of the earth, the atoms in the apple are approximately the size of the original apple. Like if the apple becomes earth, then as the apple in front of the earth, the atom is in front of the apple. And just to estimate the size and the number of atoms in the given material, here we have a question. How much time will you take to count the number of atoms just in 12 gram of carbon? A small piece of carbon, that is just 12 gram of carbon is given to you. And hypothetically, if we assume that you can count down the number of atoms in that piece of carbon and the speed of counting is say 1 number per second, then how much time will it take to count the number of atoms in a small piece of carbon? Like if we are to count 60, we'll take 1 minute. If we are to count 100, we may take nearly 1.5 or so minutes. So if all the atoms in carbon, they need to be counted in a small piece of carbon, that be 12 gram. Yes, may I please have your responses? Do we need a few months or a few years to count that number? If we keep on counting it day and night, 24/7, all the time, just counting and counting and counting, and imagine how much time will you take to count 12 grams of carbon atoms? Yes, anyone who would like to answer? May it be a few days, a few months, a few years. Yes, my friends, you can use the chat box for the response. Okay, fine. Surprisingly, this will take 1.9 into 10 raised to power 16 years to count the number of atoms in just 12 grams of carbon. And imagine the age of universe is estimated to be 13.8 billion years. And this figure is much beyond the age of universe itself. So we can use this type of analogies, we can discuss this type of analogies with our students to give them an estimation that how large the number of atoms are present in a small piece and how small the atom would be. That in a small piece, this much number of atoms can be accommodated. Similarly, for a typical human of 70 kg, there are almost 10 raised to power 27 atoms that are present. Another way of saying is it's 7 billion atoms are present in one average human body. More than 10 million hydrogen atoms would fit across the head of a pin. Let's consider another analogy. Here we are talking about the Earth, our huge, magnificent planet. And this Earth is a very, very tiny part of the solar system. Our solar system, it's a very, very tiny part of the Milky Way galaxy. And in Milky Way galaxy, 250 billion stars are present. In the observable part of the universe, 2 trillion galaxies are there. And in the observable part of the universe, 10 to the power 24 stars are there. That is 10 with 24 zeros. This much number of stars are there in the whole of the universe. And surprisingly, this much number of atoms, as there are stars in the observable universe, this much number of atoms that can be accommodated in a very small bucket of water. This bucket of water, which will be around 18 liter, that will have 1,000 times more molecules than the number of stars in the observable universe. And the number of atoms is even 3 times as each water molecule that is made up of 3 atoms. So one bucket of water, that is 1,000 universe of stars. Now coming to the next part, that atoms make everything. What makes up atoms? As now we know the atoms are not indivisible. They are having further subatomic particles, electrons, protons, neutrons. We end up here with 3 particles. But again, surprisingly, there are more than 200 subatomic particles that have been detected so far in the atom. If we consider these 3 fundamental subatomic particles, proton, electron, and neutrons, then for the beginners, we can use this PEN pen, where P for proton, E for electron, and N for neutron. And as here, the charge and mass of the neutrons and protons, the mass of proton is 1 unit and charge is +1 unit. Mass of electron is considered to be negligible because it is 1837 times lighter than that of a proton and its charge is -1 unit. Neutron, 1 unit of mass and no charge. Now here, see on the slide, atomic number is equal to number of protons and number of protons is equal to number of electrons. Anyone who want to comment on the information given on the slide, that atomic number is equal to the number of protons is equal to the number of electrons? Any comments on this information? Am I audible?
Yes, you are very much
Yes, ma'am,
audible.
you're audible.
Please
Thank
carry
you so
on.
much.
Yes, ma'am.
Yes, anyone who want to comment on this slide, atomic number is equal to the number of proton equal to the number of electrons? Okay, fine. There is some discrepancy on the slide. First, okay, I got a response that is it always, because in some it changed, yeah. First, coming to this question, I could ask this question to you, the same question, following the different levels of cognition. Identify the discrepancy in the above slide, that is analysis. If I ask the same question as, is there any error in the given slide? That's the evaluation, because there you have to give your decision whether some error is there or there is no error. And then in the third way, I could have asked the same question using the partial information given on the above slide, prepare a slide showing the complete information. Now that's a creation type question. So my dear friends, kindly evaluate your questions before putting the question paper, before designing the learning outcomes, that which level of cognition they are catering, and follow the question paper design accordingly. So same question, and it can be asked in different ways, catering to the different levels of cognition. Now coming to the error in the slide, it was written that atomic number is equal to the number of protons and is also equal to the number of electrons. Here terms and conditions apply, as it's not always true. If we see on sodium atom and sodium ion, as I didn't mention that it is for the neutral atoms. For sodium atom and sodium ion, in case of atom, number of electrons and protons is equal, that is 11 each, and atomic number is also 11. But when it forms the sodium ion, an electron is lost. In sodium ion, we are left with 10 electrons and 11 protons. In this case, the number of electrons and number of protons is not equal. So what would be the atomic number of sodium positive ion? Will it be 11 or will there be change in the atomic number, as in this case the number of electrons is 10? Number of electrons is 10, protons 11, and in sodium ion the atomic number is 11 because atomic number is equal to protons. This is universally true, but may not be equal to the number of electrons in case of ions. As in case of ions, for cations, the number of protons is greater than that of electrons. For anions, it is reverse, that the number of electrons is greater than the number of protons. So when the ions are formed, only the number of electrons change. There is no change in the number of protons and there is no change in the atomic number. Next, coming to mass number and atomic mass. Mass number is the sum of the number of protons and neutrons, and it's a whole number, as number of protons and neutrons is always the whole number. Atomic mass, it's the average relative mass of the atom of an element considering all the isotopes as compared to the mass of an atom of carbon-12 isotope. It may be fractional. As an example, the atomic number of sodium is 23, as it contains 11 protons and 12 neutrons, whereas its atomic mass is 22.98976 AMU, and which is roughly taken as 23. Now, again, my dear friends, here you have a slide with mass number of hydrogen 1 and atomic mass of hydrogen as 1.007. And mass number of chlorine as 35, as there are 17 protons and 18 neutrons, and atomic mass of chlorine is 35.5. Again, there are some discrepancies on this slide. Anyone who would like to mention any discrepancy? Any error on the information in the slide? That mass number of hydrogen is 1 and atomic mass of hydrogen is fractional, that's 1.00. Any responses? Okay. The first point is, it was mentioned that the mass number of hydrogen is 1. As we all know, there are 3 isotopes: protium, deuterium, and tritium. So it need to be mentioned that which isotope we are considering, because the mass number is different for the 3 different cases. Similarly, in case of chlorine, it's chlorine 35 and chlorine 37 with the mass number 35 and 37 respectively. Another point is, in case of chlorine, see here, it was written there are 2 isotopes of chlorine, chlorine 35 and 37. Then it's written there are 2 stable isotopes of chlorine. Only just one word stable has changed the entire sense. There are 2 isotopes of chlorine means only 2 are known, not more than 2. And there are 2 stable isotopes of chlorine. 2 are known to be stable, but actual number is much more than that. And surprisingly, again, 25 isotopes of chlorine are known. Another point. Again, here it is mentioned that the mass number of hydrogen or protium is 1 and the mass number of chlorine 35 is 35. Is there any discrepancy while mentioning the atomic mass? Atomic mass of hydrogen is mentioned here. Atomic mass of chlorine is also there. We take its mass as 35.5. Any discrepancy here? Any error in writing the mass number like this? Atomic mass of chlorine is 35.5. As we all need to discuss such possibilities of errors with our learners also. See here, the units were missing. Along with the mass number, no units to be mentioned as it is the number of protons and neutrons. But with atomic mass, we need to mention the units. Now, in this case, the mass number is written in 4 different ways, 1, 2, 3, and 4. Out of these 4 different ways of writing the atomic mass of hydrogen or atomic mass of chlorine, out of these 4, which are the correct and which are the wrong representations? All the learned educators kindly wake up. Out of these 4 different ways of representing the mass number, anyone who would like to answer which are the wrong and which are the correct ways? The first one is wrong, as no units are mentioned. With the second one, U is mentioned, that is a correct way. That's considered to be the unified mass. In the third one, AMU is written, that is atomic mass unit. That's also the correct way of writing. But in the fourth case, gram is written. Atomic mass is not to be expressed in gram. If we use gram, it must be gram per mole. As if we take atomic mass of hydrogen nearly as 1, it's not 1 gram, it's 1 gram per mole. 1 mole of atoms, they weigh 1 gram. It's not the 1 atom which weigh 1 gram. Now, what for 1 U or 1 AMU? Here, atomic mass of hydrogen 1.00784 U or AMU. U or AMU are one and the same thing. But if we write it as mass of 1 atom of hydrogen is 1.00784 gram, it's absolutely wrong way of representing. As mass of 1 atom of hydrogen, this is 1 unit. 1 unit, the value of this 1 unit is 1.67 into 10 raised to power minus 24 gram. So whenever we say it is 1 unit or it is 1 AMU, it doesn't mean 1 gram. It means 1 unit, multiply the value for 1 unit. This is 1.007 into 1.67, 10 raised to power minus 24 gram. This is the actual mass of 1 atom of hydrogen. Same is for proton also for 1 unit. See here for carbon also. If we say it is 12 U or 12 AMU, it's fine. But if we say it's 12 gram, it is not. The mass of an atom of carbon is 12 into the value for 1 unit. Similarly here, we have a very simple question here. How much is the charge on the stable magnesium ion? How much is the charge on the stable magnesium ion? This is the simplest possible question that I would ask. There's a question in the chat box that why in grams not written, it's in both question, because ma'am, one gram is not for one atom. I've written here for one atom. If we say mass of carbon is 12 gram, it's the mass for 1 mole of carbons, not for one atom. So it should be written as gram per mole. Yeah, you have written that mole part is deleted. No doubt the mole part is deleted, but at least the students must know the value for 1 mole. If they know what is 1 dozen, just only this information is required at this stage. If 1 dozen is 12, 1 mole is 6.02 into 10 raised to power 23. Nothing more than that is required. And I don't think that's a very difficult concept to be known by the students. Yes, coming back to this question, how much is the charge on the stable magnesium ion? Yeah, it's written +2, +2. Anyone else who want to respond it in some other way other than +2? There are 2 responses in the chat box with +2. Fine. Now look at this. Should it be +2 or +2 unit? Does it make a difference when we write it as +2 or +2 unit? The two things are entirely different. Let's see. You have brought 1 packet of chips. That packet of chips weighed 12.2 grams. What will you say? You have brought 1 chips or you have brought 1 unit of chips, that is 1 packet of chips. Will it be right saying you have brought 1 chips or it is 1 packet of chips? It's 1 unit. And 1 unit, in this case, the actual value for 1 unit, as it is given here, it is 12.2 grams. Suppose a chips packet that weighs 12.2 grams. When you say you have bought 1 unit of chips, 1 packet of chips, that means you have bought 12.2 grams of chips. Similarly, when you'll buy 2 packets of chips, you buy 2 units. And the actual value for these 2 units is not 2 chips, it is 12.4 grams of chips. Similarly, for 3 units, it is 3 into 12.2. For 4 units, this is 4 into 12.2 grams. So while writing it as 3 chips or 3 units of chips is entirely different. So is the difference when we write it as charge as +2 or +2 unit. Now coming to proton, it has 1 unit mass and +1 charge, +1 unit charge. The value for this 1 unit, as we have discussed in case of hydrogen, it is 1.67 into 10 raised to power minus 27 kg. And 1 unit of charge is 1.6 into 10 raised to power minus 19 coulomb. So when we say the charge on magnesium is 2 units, 2 units doesn't mean +2 charge. 2 units means the charge is +2 into 1.6 into 10 raised to power minus 19 coulomb. It is to be multiplied by its actual value. +2 charge and +2 units of charge are 2 entirely different things. Similarly, for the 3 and 4 protons, we can multiply the value of 1 unit with 3, multiply the value of 1 unit with 4. In case of mass, multiply it with 1.6 10 raised to power minus 27 kg. In case of charge, it's to be multiplied with 1.6 10 raised to power minus 19 coulomb. Hopefully, I'm clear in this. Any question from your side? Okay. Now coming to the next part, that this concept of teaching the atoms and their fundamental subatomic particles, we can follow the different pedagogies. As here we have used art integration as an effective pedagogy to promote the joyful learning. And dear educators, CBSE has announced art integration as a pedagogy, as a principal theme of training for the current session, that is 24-25. This is a CBSE theme for training, that is art integration learning. This concept can be integrated with art. It may be in any form. May it be visual arts, performing art, drama, dance, role plays, or any other form. Let the child express in whatever way he wants to express, but he must express. Give him the opportunities to express in whatever way he is comfortable with. As here's an example of an assessment technique, artistically designed, beautiful assessment technique, which can be given to the students. And another picture you can see, the students can prepare such type of cards for their teachers, or they can be displayed in their classrooms. Here we can use the mind maps also. The teacher can use the mind maps while teaching, and the same mind maps the students may be asked to prepare. It would be better if we ask the students to prepare the mind maps instead of showing them in the classroom, because if the student is not interested in doing a particular topic, but he is good in arts, and he wants to go for the beautiful colors and artistically designed sheets, he'll have to explore the information. इसको कहते हैं ना चाहते हुए भी वो chapter जरूर पढ़ेगा, because he need to retrieve the information from the chapter to come up with this designed mind map. The mind maps, they can be used and they can be displayed in the classroom itself. Then the other forms of art, they may also be used. As you can see here, a beautifully written poem on the atoms family. They are so small, they are round like a ball, they make up the air, they are everywhere, can't see them all. They are tiny and they are teeny, much smaller than a beanie. They never can be seen, the atoms family. Together they make gases and liquids like molasses and all the solid masses, the atoms family. If the student is good at singing, given the opportunity to express in that way also. Let's have some example.
Ma'am, there is no audio.
Let me check then. Is it audible now?
Yes, ma'am. Now it's audible.
Atoms are the basic building blocks of all matter. They're extremely small, make up everything in our universe. Stars, these bananas, our entire body, all made of tiny atoms fit together differently. Atoms are made up of three particles called electrons, protons, and neutrons. Electrons are the smallest, their charge is negative, spinning really fast all around the nucleus. The proton's positive and located in the center, forming the nucleus with neutrons that have no charge at all. When particles amass different, makes various elements. One proton, one electron, the simplest atom's hydrogen. Every element has its own atomic number, tells us how many protons located in its center. Less protons means less mass, like hydrogen, that's a gas. It's less dense in the air, one proton in the nucleus. Because protons have a strong positive charge, push each other away, bubble back with a strong nuclear force. Balance makes atoms possible, everything in the universe. Different atoms clumped together are known as molecules.
So, dear friends, the final idea is whether the student is interested or not interested in learning. It is now our skill to make him learn the things. It's our skill to develop the interest for the learning, whatever way we follow. And on a lighter side, just look at this picture and don't mind if your student come with this type of response. Is this visible or should I read it for you? That a student forget to bring the model of an atom. The last date to submit was there. And he go to the teacher to say, do I at least get 99.9% partial credit for the empty space? See the innocence of the child that 99% of the space is empty. And at least he's asking for that empty space, the credit for that empty space. Now coming to the different models of the atoms. This is a timeline of the models as started with Democritus, who has given the term atomos. Then John Dalton, that is, he has given the atomic theory, plum-pudding model by Thomson, planetary model by Rutherford, then Bohr's model, and finally the quantum mechanical model by Schrödinger. In this chapter, we'll be dealing with the three models in detail, that is Thomson model, Rutherford, and Niels Bohr model. And interestingly, Niels Bohr is the student of Rutherford, and Rutherford is the student of Thomson. So this atomic theory, it was inherited from the teacher to the student and then to the next student. Now, before this the subatomic particles, the John Dalton, it came with the Dalton's atomic theory, where he suggested that the atoms are indivisible particles. It explained atoms cannot be broken down into the further smaller particles. However, the discovery of these subatomic particles disapproved the postulates proposed in Dalton's atomic theory. The discovery of subatomic particles led to the search how the subatomic particles are arranged in an atom. J.J. Thomson was the first and one of the many scientists who proposed the models for the structure of atom. It had been known for many years that the atoms contain negatively charged subatomic particles. But the term electron, it was not coined by Thomson. The term electron for the fundamental unit of electricity, it was coined by G.J. Stone in 1891. And during the cathode ray tube experiments, negatively charged particles were discovered by J.J. Thomson in 1987. He called them corpuscles, but they were more commonly then called as electrons, the name G.J. Stone has coined. As for this model of an atom, we normally deal with these first two or at the most these three postulates. An atom consists of a positively charged matter. It consists of a positive sphere in which the negative electrons are embedded randomly. An atom as a whole is electrically neutral because the negative and positive charges are equal in magnitude. Now, this is the point where the students, they mostly commit a mistake. As it is highlighted here, that the magnitude of the positive and the negative charges is equal. What the students normally write, the atom is considered to be neutral because the number of electrons and protons is equal. So in this model, if the child is writing the number of electrons and protons is equal, then the postulate is not correct because at that time the protons were not known. The mass of an atom is uniformly distributed throughout is another postulate of this model. And interestingly, neither Thomson nor his colleagues has given this analogy of plum pudding model or watermelon model as we know it today. That in plum pudding model, just like the raisins are embedded in the pudding, or in the watermelon model, just like the seeds of the watermelon are embedded in the red edible part, this analogy has been used by the other scientists to make the model accessible to the layman, but neither Thomson nor his colleagues ever used this analogy. Although the Thomson model was not an accurate model to account for the atomic structure, it had no experimental evidence, failed to explain the scattering of the alpha particles by the thin metal foils, but it proved to be the base for the development of the other atomic models. Now, the Rutherford's alpha scattering experiment, he conducted an experiment by bombarding a thin sheet of gold with alpha particles and then studied the trajectory of these alpha particles after their interaction with gold foil. He directed high energy stream of alpha particles from a radioactive source at a thin sheet, which was around 100 nanometer in thickness, of gold placed in a circular zinc sulfide screen, and he made certain observations that contradicted Thomson's atomic model. As here we can see the observations and conclusions, and most of the alpha particles, they are passing straightway as if nothing is present on the way. And what is the conclusion on the basis of this observation? That atom on the most of the space in an atom is hollow. Very few alpha particles, they were deflected by the smaller angles. And what does this indicate? That the nucleus carry the positive charge, and still very few alpha particles, they bounced back by the larger angles, which indicate that the nucleus is heavy. And on the basis of these observations, this model was proposed that the alpha particles which bounced back, it is due to the presence of the massive nucleus in the middle, and the mass is not uniformly distributed, but it is concentrated in the middle of the atom around which the negative electrons are moving, just like the planets revolving around the sun. This is what we normally teach in Thomson's model. And if we end up teaching the model at this point, we are just imparting the knowledge. We need to develop their competences, their skills, their thinking abilities, the learning to be inquiry-based learning, make them learners think about the things. And for that, we need to discuss the rest of the details also. That what is the role of the lead box here? What was the source of alpha particles? Why Rutherford had taken alpha particles? Why slit is required? What should be the material of the slit? Why gold foil was taken? Why not other metal was appropriate in that case? Why thin sheet of gold? Why zinc sulfide screen? Why circular movable zinc sulfide screen? Can lead be used instead of gold? This type of questions, they can be used in the classrooms for the brainstorming sessions. Like if we discuss with the learners, what's the role of the slit? That's just to narrow down the beam of the alpha particles. We have given the information to the students that the radioactive material, which is the source of the alpha particles, it is placed in the box made up of lead, because the lead is a very dense metal and it absorbs most of the radiations. And then the slit is required to narrow down the beam. Then another question which can be asked, what should be the material of the slit. If slit is to narrow down the beam, it should also be made up of the lead so that the beam is narrowed down and the alpha particles, they should not pass from the rest of the portion of the slit other than that tiny hole. So provide the situations to the students so they think over and over to come up their conclusions. That's a constructivist approach. Make them to construct their knowledge instead of just pouring in. Similarly, we have seen here in the Rutherford's model, the metal taken, it was gold foil. We discussed with the students why gold foil, as it is highly malleable, and the metal was required which can be beaten into the sheets as thin as possible so that the minimum number of atoms come on the way to the alpha particles. So the students, they can be asked this question, the brainstorming sessions can be conducted. Can lead be also used instead of the gold? What would happen if the lead would be used? Then again, if Thomson's model, another example for a brainstorming session, if Thomson's model of an atom would have been the correct a representation of atom, then what would observation in Rutherford's experiment? Let the learners think over. Like Rutherford didn't perform the experiment with a view that the nucleus would be discovered. At that time, Thomson model was known. And according to Thomson model, the whole of the mass is distributed uniformly. If the whole of the mass is distributed uniformly, the positive charge is distributed uniformly. Then if the alpha particles would pass through that, what would be the observation? Here you can conclude this observation after that brainstorming session that based on the Thomson model of an atom, it was assumed that there was nothing dense or heavy inside the gold atom to deflect the massive particles from their path. However, what Rutherford actually observed didn't match his prediction, so a new atomic model was needed. And Rutherford himself described the results by saying, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fire a shell at the piece of tissue paper and it came back and hit you." Here's an example how the same topic, it can be taught to the learners by following the different pedagogies, as we can use the art integrated learning, the examples discussed in the previous slides. ICT, blended mode, flipped teaching, as in ICT, we are using these diagrams over the slide, or we can go for the flipped teaching, where the students, they go for the low order thinking skills, that is the remember and understanding part by watching the video, and then in the classroom, the high order thinking skill questions are discussed, the brainstorming sessions are conducted. Experiential learning, inquiry based learning. As a part of experiential learning for this model, here we can provide the situation to the learner, like if we keep a net in the middle, a screen of net, and the students are asked to throw the tennis balls from one side. Suppose a student throw 100 tennis balls through that net, and 95 of the tennis balls, they cross the net in the first case, and just 5 tennis balls, they bounced back. In the second situation, only 5 or 10, 10 tennis balls, they crossed the mesh, and the rest of the tennis balls, they bounced back. So in the first case, the mesh size is large, as it is the second figure on the screen. In the second case, the mesh size is small, which is the first figure on the screen. So this type of situations, they can be related to the Thomson model, to the Rutherford model, and the situation would be similar to the broader mesh from where the most of the alpha particles, they would pass. These are the limitations or the drawbacks of Rutherford model. It failed to explain the stability of electrons in a circular path. He stated that electrons revolve around the nucleus in a circular path, but the particles in motion, they undergo the acceleration and cause energy radiation. Eventually, the electrons should lose energy and fall into the nucleus. It should happen only in 10 raised to power minus 8 seconds. And the atom should collapse in this much time only. As the atom doesn't collapse, so the atom is stable, but this model failed to explain the stability of the atom. This drawback of Rutherford model, it was resolved in the next Bohr model. And to resolve this issue, Rutherford changed only one word, that is a continuous emission to discontinuous emission, or the circular path to discrete, stationary, quantized circular orbits. The only problem with the model was a continuous emission. Actually, the energy is not emitted out continuously, it is emitted out discontinuously. And these orbits, they are the quantized orbits. Now, to understand what are these quantized orbits, let's consider the figure number 2 on the left side and figure number 4 on the right side. As you can see here in the figure number 4, there's a staircase. If a person has to go upstairs using this staircase, and suppose the average height of his staircase is 9 inches, he can take a step of 9 inches, or another step, another 9 inches, he can stand at a height of 18 inches, still another step of 9 inches, and he can be at a height of 27 inches. So he can be at 9 inches or 18 inches or 27 inches from the ground, but he cannot stand at a height of 15 inches or 20 inches or 25 inches by his own choice. There are predetermined, predefined, discrete, discontinuous values. That is, in this case, for a staircase, it is 9 or 18 or 27 or any other multiple of 9 if the person is going upstairs using the staircase whose standard height is 9 inches. These are the quantized values, the discrete, discontinuous values. On the other case, if we see the figure number 2 on the extreme left side, if the person use the ramp, on the ramp, this is the choice of the person that he take a step of 1 inch or 2 inch or 5 inches, maybe 5.1 inch, 5.2 inches. No predetermined values, no fixed values, any value of one's choice. So, according to Rutherford's model, energy is emitted out continuously. Any value of energy could be emitted, and the electron can be at any distance from the nucleus, and so following the spiral path, emitting the energy continuously, it should fall into the nucleus, and the atom should collapse. But what Rutherford said, it's not the continuous emission, it's a discontinuous emission, and the electron, it emit or absorb energy only when it change its orbit, only when it change its staircase from first stair to second stair, and it cannot emit any value of its own choice, only the difference which is there between the two levels. As if a person go from one stair to another, only 9 inches is allowed. If he take a step of 10 inches, he'll fall back to 9 inches. If we take the step of 12 inches, again, he'll fall back to 9 inches. And if we take the step of 8 inches, he'll be on the ground floor itself. So 9 means 9 here. So the concept of continuous emission, it was replaced with the discontinuous emission. The circular paths, it was replaced with discrete, stationary, and quantized circular orbits. Another point we noted here, that these orbits are the stationary orbits. Stationary doesn't mean that the electron come at rest. It's all the time moving and moving. What does stationary mean here? Stationary here means the energy of the electron that become constant when an electron is moving in a particular orbit. As long as it is moving in a particular orbit, its energy is not going to change. Energy is constant. That means the orbit is stationary. Stationary doesn't mean the electron is at rest. It's not at all. So here we end up with these models. Here is another example that if we give this type of assessment to the learner, which level of cognition it will cater to. As here the atomic number, mass number, number of protons, number of neutrons, they are to be analyzed. This is analysis type question. And let's have another video that is about the models of the atoms.
Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton did experiments and said, I think it's clear atoms are tiny indestructible spheres. Thomson worked with cathode rays, said I disagree. A plum pudding model makes much more sense to me. A new chapter in atomic theory started to unfold when Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked them off the track. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg, and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place.
And here comes the most awaited slide of the session. Thank you so much. Any question from your side?
Thank you, ma'am. Thank you so much. It was a lovely session, very well explained by you, and we really enjoyed the entire session. Any questions? Any questions from our participants? So sincere thanks to my resource persons who have shared their knowledge and expertise with us in such an excellent way. Thank you, A.K. Sharma, sir, for providing us this lovely platform. So let's conclude today's session with the Shanti Mantra.
Just
Just a minute.
if you
Yes,
want,
sir.
you can ask anyone who want to ask the question, because in this session I have seen nobody asking the question. So can I take 2-3 minutes?
Yes, sure, sir. We can take 2-3 minutes. Anyone who wants to ask a question?
Actually, I was reading somewhere that what is good listeners? What are the characteristic features of the good listeners? And in that, the first thing is I have read about the attentiveness, that those who are the listeners, they should be very much attentive. They should show genuine interest in what the resource person is saying. And second is that the learner should come with the open-mindedness. That is, they should approach the conversation without any judgment. And whatever the speaker is expressing, let him express freely, and then they have to give their own comments. Third is empathic. The listener should be empathetic. He should understand the speaker's perspective also and emotion also, and he should try to put himself in his shoes. And there are number of non-verbal cues are there, because you have seen that they are using body language. You have seen both resource persons, they were also using body language. they were trying to maintain the eye contact, and they were engaged, and they were engaging our teachers. So my submission is that all the listeners, they are very patient, no doubt, but they should also reflect back to whatever they have heard to ensure that whether they understand or not. So it is not that they are not children, like वो चला दिया वो लगा दिया और भाग गए, वो चल रहा है. Maybe that some of you may be, but I don't expect that any teacher can be of this type. So please show the respect, curiosity, and feedback, which is very, very essential for our resource person. Remember, they are all one of you. They are all teachers. We are not taken any from them anywhere. So I request all the listeners, all the teachers who are attending, please give their comments, maybe in one line, maybe in a very short. So whatever you want, you can give. From next, not today, from next time, please give your comments, maybe in comment box. If you cannot speak, you can give it in the comment box. But I'll be very happy if you give your comments after coming on a live video session. Thank you very much.
Thank you,
Please.
sir. Thank you so much, sir. So let's conclude the today's session with the Shanti Mantra.
पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते. ॐ शान्ति शान्ति शान्तिः. हरिः ॐ. श्री गुरुभ्यो नमः. हरिः ॐ.
Thank you so much.
So thank you. Thank you very much.
Thank you, sir.
Thank you very much. Amit, thank you very much. And Hardeep Kaur,
Thank you, sir.
You have wonderfully explained. And I was remembering of my own days when I used to study physics and chemistry. So you have given a very clear picture of your subjects. You are all superb and wonderful. So once again, on behalf of all the participants, I convey my heartful thanks and regards to Harpreet Kaur and
Thank you,
Amit
sir.
Jain.
Thank you so much.
Simply
Thank you, sir.
superb.
Thank you, everyone.
Wonderful job you have done.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you so much, sir. So I request all the participants, they can leave the meeting now.
Was you have good bad?
Very good.